Earlier we discussed how we define momentum flux correction factor denoted as beta. Now we try to do one or two exercises, and these exercises are very necessary to be done because our subject demands that whatever we are trying to do, we should also know how to apply them, how to work them out if we need to. So simple exercise, we try to do it here, and it is taken again from the same book. So the purpose is to show that if one has to calculate beta, how do we do it? And that is amply clear and evident from this small assignment that is given. So this is a question. Example means exercise, and calculation of momentum flux correction factor for laminar flow. When they mention laminar flow, it is obvious that beta is not going to be equal to 1 or close to 1. It will be slightly different so that the flow is developed and laminar and not turbulent. Consider laminar flow through a very long straight section. Obviously, it needs time, it needs distance for the flow to develop, to take its final shape. And this takes place in a cross section of a round pipe. It's shown, well, later on we may, some of the things that we mention here, we will be discussing in the later part of this course as well, as we go along to develop what we call as equations of motion, and eventually leading to development of Navier-Stokes equations and their applications. It is shown in this chapter that the velocity profile through a cross-sectional area of the pipe is parabolic. So we can see it from here that the velocity profile is parabolic because the term here is a square term, and that is a typical reflection of a parabolic shape. And R, here the term they have defined it, R is the radius of the inner wall, V average is the average velocity. As we can see, they say that calculate the momentum flux factor through this pipe of the section, and it is sketched as this. So if this is the sketch of the fluid flow, radius, you can see small r is the radius of the fluid flow, whereas capital R is the radius of the pipe in which the flow is taking place. So that is the difference why two different terms have been used for radius, for the same radius, for the same thing in a same fluid flow situation. One belongs to the pipe, the other one is the radius that vary and that stays within the flow field, as is shown here. So velocity profile over a cross section, and you can see that this is parabolic in shape. The flow is incompressible and steady, so that's the first thing that we see or we assume. And if we say that this is incompressible and steady, it makes our working simple. We don't have to worry about the compressibility, the density becomes constant and so on, and it is steady, so that is with time there will be no change. The control volume slice through the pipe normal to the pipe axis is as shown in the picture. We have seen that. And then now we go to the analysis. And analysis means to the working. The small area by our small formula of geometry is equal to 2 pi r into dr. And again this r is the radius of the flow of the fluid, not the radius of the pipe in which it is taking place. And beta by formula is equal to this part, and when we substitute the values we obtain this, and we have to calculate, because what is the maximum value that flow can take. It can take from 0, if 0 is the center of the pipe, to the maximum, which is end of the pipe radius, where the solid body, where the fluid meets the solid body, and that is R. So these are the limits of small r of the variation. And when we integrate it, this is a simple integration, and we obtain these values, and they are very simple, and you can see the value beta is calculated to be 4.3, which is 1.33, and we have seen the flow. So simple enough to calculate beta. It's not too complicated, reasonably simple. For turbulent flow beta, then it may have significant effects in inlet and outlets. लेकिन turbulent flow situation, ये जो हमने consider किया, this was laminar flow situation, और बीटा की वैल्यू आपने देखा कि 1.33 यानी 4/3 आई. लेकिन we have already mentioned कि turbulent flow उस वक्त होगा जब बीटा is equal to or very close to, let's say 1. लेकिन जब उस वक्त अगर ऐसी सिचुएशन पैदा हो जाए, so it can be significantly, the flow field can be different at inlet as well as at the outlet, and it is wise to include beta in all momentum control volume problems. So it is essential that if the control volume integral is considered in calculation of forces that are acting on a flow, then we include the consideration of beta in equations of motion that we calculate.